I will introduce Professor Lucimara Roman to you now. It's a pleasure to introduce her once again. She holds a PhD in applied physics from the University of Linköping in Sweden. She's a pioneer in the research of organic solar cells in Brazil. She authored more than 120 papers that were published in high impact publications. She has a H factor above 20. She is the director of the Nanostructured and Electronic Devices Laboratory at UFPR, and she's the Vice Dean for Graduate Programs at UFPR. I also would like to present our co-chair for this session, Professor Luis Pereira Ramos. He holds a PhD from the Ottawa Carleton Institute of Biology of the University of Ottawa, Canada. He does research on biofuels, and he's has a research productivity scholarship from CNPq since 1993, and has a H factor of 35 in a total of about 4,000 citations and over 130 articles published. He's a full professor in the graduate program in chemistry in the UFPR, just retired, and at the chemical engineer graduate program. He's a member of board in the INCT Energia and Ambiente, and associate professor of the American Chemical Society's Energy and Fuels magazine since 2012. Professor Lucimara Roman, the floor is yours.
So, good morning, everybody. Now, we are going to start with our section number 7. So I will share my screen and to present to you what we are going to see today. Let's see if I can do it. Are you seeing my screen? Yes, I hope. So today we are going to start our panel in Sustainable Development Goals, a global scientific conference at the UFPR. Section 1, clean energy. So from these 17 goals, we are on number 7, affordable and clean energy. And today we are going to have 4 presentations, keynote, and 2 shorter presentations. And then we are going to have a discussion, and then we close 12:30. So the first talk, we are going to welcome very much Professor Satinder Brar from the York University in Canada for our keynote talk. Professor Brar is the James and Joan Love Chair in Environmental Engineering, and her research is on the intersecting areas of environmental engineering and its impact on the overall well-being of the global community. She has got many national and international awards, having best honored on her such a Best Paper Award in 2021. EDGE Principles Processes Wastewater Medal in 2019, honored by the Water Environment Federation. She leads the bioprocessing and nanoenzyme formulation facility at York University and supervises many students. She has published more than 390 articles and 12 books, and at least 55 invite talks. So welcome very much, Professor Brar, and you can present you stop sharing to open space for you.
No problem.
Very welcome.
Thank you so much for your
It's a pleasure to have you here. Yeah.
So yeah, just a moment. I hope everything is visible. It's okay, or
yeah, it is. Yes.
Or should I do you see my full screen or?
Yes, it's very good.
Okay. Okay. Thank you so much, Professor Lucimana. That was a wonderful introduction. So welcome back, everybody. I think this conference is an interesting perspective on United Nations Sustainable Development Goals. And I would like to, in fact, thank Professor Sokol, Professor Carvalho, and all his group, because I know many of them, we have been working together for almost more than a decade now on different perspectives of biomass value addition. So thank you so much. I know that Professor Sokol is not there here today, but I should thank him for this invitation. And I think this is a very relevant and apt conference in the given time perspective. So here I am to present to you something on biohydrogen. So we will try to understand if biohydrogen production, is it a far-fetched reality? And here with me, I have my senior PhD students, Carlos and Rahul, who are also there in the audience and who have been part of this presentation. So let me start with an overview of the biohydrogen. So biohydrogen in biofuel industry, if we would consider, it also occupies an important role amongst so many other biofuels, such as biodiesel, bioethanol, and biobutanol, because otherwise, we had to deal with almost all of us are aware of the GHGs in terms of CO2 equivalent, which is approximately 8 gigatons from the fossil fuels. So now biohydrogen, it is being considered as an alternative to solve energy issues. Why is it so important? Because of the fact that it is microbial based as any other biofuel. It has high energy density, so you can get more energy per unit mass, as well as there is no carbon, so there is no question of any GHG production. And in terms of sustainability, of course, it's sustainable because, as we walk through, you will see that there is a possibility that we would have a circular economy type of model. And in terms of scope or applications, of course, it can have wide-ranging applications from the aviation industry to the automobile industry. Now, since I'm from Canada, let me give you the status. What is happening in Canada here? So in Canada recently, the government of Canada launched Canada's Green Future Strategy or a program in which they considered hydrogen as an opportunity, and they are expecting that by 2030 there will be 6% of the delivered energy, in terms of hydrogen, and 30% by 2050. And of course, taking this into account, they are also considering, if you remember, recently there was the COP26, where of course Canada was one of the signing members on reducing the greenhouse gas emissions. So Canada expects to have a GHG reduction of about 45 megatons by 2030s, and in another 20 years, almost 200 megatons. So, of course, the most important reason behind this is because Canada has rich feedstock reserves, and there is skilled energy source, energy infrastructure assets, as well as there is a possibility of becoming, among one of the top 3 global producers of clean energy. And now, what are the pathways that are being considered in Canada across the country? So we have the general pathway that is using clean electricity, using hydro, wind, nuclear, biomass, or solar. and going through the electrolysis path, which all of us are aware, or even, you know, using the water for electrolysis, as well as steam methane reforming, which again, of course, is derived from the fossil fuels, from natural gas, or going to pyrolysis to, you know, purify the CO2 captured and then finally lead to hydrogen. And of course, last but not the least, biomass is also being considered as an important aspect or an important feedstock in order to produce this energy through reforming, so that it could finally lead to hydrogen production. Now, what is happening at the policy level in Canada? We actually, at present, since I just introduced you to the fact that we recently launched the Green Future Drive in Canada, we do not have any policy per se. It is rather a strategy. So amongst all the strategies to have a green future, which includes renewable energy like wind, solar, etc., hydrogen is also being introduced as one of the low carbon fuel strategies, okay? And of course, because of the fact that Canada is also planning to put a carbon pollution pricing, and then there would be vehicle emission regulations, zero emission vehicle mandates, and there is a plan to even go for emission-free zones, and even there is a lot of you know, rekindled interest in natural gas networks. So moving on from the Canadian perspective, now let me bring you to the technical perspective of biohydrogen production. Of course, biohydrogen can be produced through two routes. We can have the biological route or the thermochemical route. In biological, we have the biophotolysis, the dark fermentation, and the photofermentation. And thermochemical normally comprises the gasification and pyrolysis. Now, let me nail down for you after this, what would we expect as a theoretical yield if we go through all these different you know, types of biohydrogen production. So you would see, you know, the maximum we expect is 12 moles of hydrogen, for example, from direct photofermentation and indirect biophotolysis. This is what we expect, but when we go to the experimental scale, this is not what we achieve. And of course, it's not easy to do that, because we should not forget that in all the biohydrogen production, we also have the biomass. So biomass also comprises some amount of hydrogen. So we are technically, you know, you can say channelizing some amount of hydrogen into the biomass as well. Now, in terms of biohydrogen production, typically which type of microorganisms are involved? The most common ones are Enterobacter and Clostridium. And of course, now there is a trend to go towards mixed microbial consortia, which was always the case. If you would recall anaerobic digestion in wastewater treatment plants, which is used as one of the steps for managing the wastewater sludge. So this anaerobic digestion always comprises mixed microbial consortia as one of the, you know, the flora for producing biohydrogen. And in terms of substrates used in biohydrogen production, so we can have all the way from industrial waste, that is wastewater, sludges, chemical waste, or we could have hydrolysates, which are derived from the lignocellulosic residues. And of course, you can have the clean substrate like glucose, starch, lactose, fructose, etc. So it's quite diverse in terms of biomass, as it is for other biofuels. So my focus would be more on wastewaters, you know, how biohydrogen production is actually taking place in terms of their production using these substrates. So let's first see how normally biohydrogen would be produced from the wastewater. So we have the industrial wastewater, which is actually, you know, a source it supplies the carbon, nitrogen, and all other micronutrients, and it gets transformed into organic acids. And of course, hydrogen and CO2 are also the byproducts. So this is typically a dark fermentation, you know. This is all happening in the dark, and you would produce only 4 moles of hydrogen through this. Likewise, if you do the same process using the non-sulfur bacteria in presence of light, again, we produce 4 moles of hydrogen. Now, this is, again, theoretical, okay? But as we move on to the experimental phase, we are reaching only 50 to 60% of the total hydrogen production that we would expect. So we are still not there in terms of their productivity and yield. And if I look at the publication on biohydrogen production using wastewaters as a substrate, this is a research conducted by one research group. Until 2020, they reported that hydrogen production, especially from wastewater, there was an increase, a gradual increase until 2020. And of course, the primary role of this hydrogen production from wastewater was to see if there is a simultaneous COD or chemical oxygen demand reduction, because that is the key perspective when we go to wastewater treatment plants. That is a goal which they want to achieve when they are producing any of these biofuels. And the same research group, when they listed the number of publications with the years in terms of the different technologies or processes that are developed for biohydrogen production. So they saw that dark fermentation was the most prominent, and it is normal that as well, because even us in our research group, we have seen that it is much more easier to do, as well as the production of biohydrogen was relatively enhanced as compared to, let's say, photofermentation. Okay, and of course, microbial electrolysis cell is also gaining importance because of the fact that it is much more cleaner to produce that way. But this technology is still at its infancy, and there are a lot of things or a lot of parameters which need to be taken into consideration. And then we have the microbial photoelectrochemical cell. So this is also something catching up from the regular electrochemical type of reaction, where we just have the microorganisms and the anode and cathode. So this technology is, again, it's just started. I think it's the interest has just started in this technology, which is still at the lab scale. I would say there are not many bench scale studies which have been conducted in this for this technology. And then they also considered what kind of, what were the key research objectives which were attained or accomplished while producing biohydrogen from wastewater. So the primary thing, perspective they saw was the reactor configuration. So most of the research articles were, their primary focus is working around the reactor configuration. Which reactor configuration would be better for producing biohydrogen production? And then, of course, comes the material. Material in this sense means like what kind of, what would be the substrate which would be used for the production of this biohydrogen. So now, having seen the fact that, of course, there is an increasing interest in biohydrogen production, still, we wouldn't say that it's easy to produce biohydrogen. There are few challenges associated with it. So let me walk you through these challenges. First and foremost is the low substrate conversion. I already showed you those theoretical reactions where we expect a maximum of about 12 moles of hydrogen, which is not achievable actually in the real conditions. And then there is the low hydrogen productivity. And another aspect is the scale of anaerobic and photobioreactors. That is something which also needs to be dealt with. And then there is the low pH. And don't forget that when we are doing anaerobic fermentation, we have the presence of methanogens. And methanogens definitely would not allow the enhanced production of hydrogen, because then a part of hydrogen is actually getting into the methane. And last but not the least is the biomass age, okay, and its washout in continuous fermentation. So that's why it's difficult to have this high hydrogen productivity due to these different challenges. And of course, there are reactor limitations as well. When we go into continuous production, the production time and commercialization is still not there in the case of biohydrogen. Just I wanted to point the importance of these different parameters here. The pH plays an important role. There could be some inhibitors present in wastewaters, especially municipal wastewaters. They are a cocktail of different heavy metals. Then you have so many other organic compounds, and it's an unknown universe in that municipal wastewater. So you don't know what you're dealing with. So you never know what kind of inhibitors you could have. Of course, the common inhibitors, which we can easily nail down, are the ones from lignocellulosics. But from municipal wastewaters, it's not easy to determine that. As well as temperature is an important factor. And of course, the redox reactions also play an important role. How much organic is being loaded in terms of kilograms per day, that is also important. And you need to supplement the alkali as well, which is important, and how much COD and BOD is there, whether the nutrients are really easily available to the microorganisms that are carrying out the biohydrogen production. So here that could be a mixed culture, or it could be the specific culture that I mentioned, that is the Enterobacter or the Clostridium. So what are the recent advances? Of course, you have already seen when I showed you the graph with publications, but I just wanted to list them here. One way research is moving in biohydrogen is researchers are now doing bioaugmentation. So sort of, enhancing the capacity of the microorganisms to degrade the biomass and produce biohydrogen. And second thing that is being considered is cell immobilization, which is a well-known established technique in bioengineering, which is, that sort of then affects the biomass age. So the cells are well adapted, and then they could carry out the production of hydrogen, let's say in a semi-continuous or continuous process. And then microbial electrolysis cell, like I just told you, is also gaining momentum. It's being considered as one of the advances to produce hydrogen. And then we have genetic engineering. Of course, the microorganisms are being genetically modified so that they can be super producers of hydrogen. So this is what is being conducted recently in terms of advances. And now let me walk you through what we have done in our lab. Of course, this work has been done long ago, because right now our focus has mostly shifted to anaerobic digestion to produce methane and increase the digestate quality, especially for municipal wastewater treatment plants. Because here in Canada, now the trend is that all of the municipal wastewater treatment plants, if possible, they should manage their sludge through anaerobic digestion. So the focus has moved towards that. And since our research work involves industries, so we have to collaborate with these municipalities to switch our focus from what needs to be done immediately. So at this point, actually, in our lab, we are working more from anaerobic digestion perspective in order to have higher yields of biogas and improved digestate quality. But in the past, I had, these are two of my PhD students who have passed out. They're out of their program, and now they're professionals in their respective fields. They have worked on biohydrogen production using crude glycerol. And this research is from one of the students. His name is Dr. Sarma, and he has published these results on hydrogen production, which you can see here on the y-axis, And then we have the concentration of the crude glycerol is actually a byproduct which comes out of the biodiesel industry. Okay, so when the biodiesel is being produced, this is like a byproduct. So it is of no use to those industries. And at that point, we were considering on adding value to this crude glycerol, and hence this project on hydrogen production was started. So as you can see, the optimum was, the optimum was reached at almost 4.5 millimoles, which is not a big amount in terms of hydrogen production. And that's what has been my entire narrative so far, that low productivity is a big problem in biohydrogen production, be it from wastewaters or be it from any other biomass. And then, because we were getting this low productivity, we wanted to see if we could improve this productivity by supplementing some other wastewaters or some other waste. So then we added, these are the list of different wastes that were added, all the way from brewery to slaughterhouse to secondary sludge to the starch industry wastewater. And on the y-axis, you have this hydrogen production here in millimoles per liter. So you can see we reached almost 120 millimoles per liter, which is a good amount, but it's not still very high, I would say, in terms of production. So eventually, then we also wanted to do this on a semi-continuous scale. So that also we achieved the semi-continuous scale. And in fact, we have a patent on this technology where we were able to go up to 6 liter per liter medium of the hydrogen. So there was a 6 times increase in biohydrogen production as compared to when we were dealing with the batch fermentation, which is of course carried out in very small scale serum bottles. And then, as we were conducting these studies, specifically using monocultures, so all the studies so far that I've reported are using only one single microorganism, that is Enterobacter species. We wanted to move on to see how co-culture would perform. So what we did was we took Enterobacter with Clostridium together, and we did some co-culture studies. So here you can see in terms of results, if we look at the hydrogen yield in millimoles per mole of substrate, we had almost 0.95 yield as a yield as compared to the monoculture where it was 0.82 or 0.83. So this was a big advantage, and we did not do any pre-treatment for our crude glycerol. So it was taken as such, as a residue, and then fermented using these monocultures or co-cultures. And likewise, we studied a combination of dark and photo fermentation in wastewater secondary sludge. And as you can, where we added, of course, the crude glycerol. Sorry, this is in French. So the crude glycerol ranging from 15 to 25 grams per liter. And we had almost at 20 grams per liter, hydrogen production of 38 millimoles per liter. Okay, and of course we produced other byproduct, which is an important byproduct, that is 1,3-propanediol. So going back to my earlier observation, what I want to tell you, despite getting this high hydrogen productivity, or yield, and the propanediol production as an important value-added chemical, still I would say that hydrogen production was far from what we would expect it to be commercialized. So we are still not there in terms of hydrogen production, but that doesn't mean that we don't continue the efforts in this direction. So like I said, in Canada now there is a lot of focus on hydrogen, be it biomass-based or be it the normal electrolysis-based hydrogen. So there has been a lot of focus on this. Of course, I'm not touching on the aspects of storage because that's another complex, a challenge to handle, and I'm sure all of us are aware of that here. So this is something which I think, which we need to look into. But at the biohydrogen stage, especially from wastewaters, I think our key struggle is always to deal with the yield and the productivity. So to answer the question which we raised, that is where we are we really far, far from the reality in terms of biohydrogen production from wastewaters? I would say at this point, we would still have to wait probably two or more decades, to get to a stage when we can actually commercialize this biohydrogen production, especially from wastewaters. Okay, but at the same time, to stay positive and in order to, of course, say that we need to go take some actions for the climate change, I would say yes, hydrogen and its applications, they could have an important role to play, in not only in terms of the improved ecosystem safety, but as well as in terms of, creating additional jobs or, improving the security in terms of energy as well for a typical country. So in Canada, that's how the Canadian government is looking at the hydrogen perspective. And I'm sure this would be the case in so many other countries as well. So with this, I think I've come to the end of my talk. And I hope I respected my time. Thank you so much. So thank you, I would say again, for the invitation. I hope I think I've respected the time. So we have time for some questions.
Yes, indeed, you respect your time. Thank you very much for that. It was very nice and interesting talk. And we are going to leave the questions for the end of the section. Is it okay?
Yeah, sure.
Okay,
no
good.
Okay, that's the way it is done. Okay.
Because then we move to the next talk. That is Professor Claudio. And then in the end, we make discussion. This is the idea.
Okay, so I will stop sharing. Yeah.
Thank you. So now we are going to move to our second talk, keynote talk in this section. That is Professor Claudio José de Araújo Mota. He is a full professor of the chemistry and chemical engineering at Federal University of Rio de Janeiro, and the current director of the institute of that institution, the Institute of Chemistry of that institute. He is a research CNPq research fellow and appointed as the state scientist of FAPERJ, Cientista do Nosso Estado. It's a prize. He was being awarded with TWAS prize given by the Mexican Academy of Science, and ABQUIN Technology Prize, and the Brazilian Society of Chemistry Innovation Prize. He has authored more than 120 scientific papers and 12 patents, dozens of books, chapters, and he also co-author and editor of 3 books and member of the several international collaborations. He is a part of the editorial board of several journals, and his current research interests are focused on the catalytic conversion of biomass and process of CO2 capture, and the conversion targeting applications on the fuel and chemical sectors. So I welcome very much Professor Claudio Mota, and if everything is okay with your sound, you can share the screen and start your. Thank you very much for your.
Thanks for the nice introduction. Can you hear me okay now?
Yes, it's very good.
Okay, okay. So thank you very much, Lucimara. I'd like to thank the organizers, Luis Ramos and the other organizers, for the kind invitation. It's a pleasure to be here to share a little bit of our research and also to know others' research. It's a very important topic. Can you see the screen? Yeah. Okay.
Let's see. Now it's in presentation mode. It's perfect.
Okay. So I'm going to talk about CO2 capture and conversion to sustainable fuels and platform chemicals. Energy is everything in our life and in our planet. It's because of the energy that we receive from the sun that life has brought in our planet, and human life that brought civilization. But this civilization that we live in is affecting our environment. So we up to now, this is the only home that we have in the universe. Maybe in the future, we can find other homes, other place to live in. But up to now, this is the only one, and we have to keep it. In terms of fuels, if you talk about energy and chemistry, you think about fuels. Since the beginning of the Industrial Revolution, we start using fossil fuels, like coal, that flourished, especially during the 20th century. But later it was not replaced, but surpassed by petroleum, that up to now, coal and oil are the main source of fossil fuels, fossil energy. This century, we will face a transition. We will use fossil fuels, but we have biofuels and hydrogen and other source of energy in our matrix, energy matrix. So this will be a transition, because one of the consequences of burning of fossil fuels is the CO2 concentration in the atmosphere. This graph shows you the amount of carbon dioxide emitted since the beginning of the 19th century. And we see an increase. And if you put the average temperature of the planet, you see mostly an exact correlation with the concentration of CO2 in the atmosphere. Today, it's about 414 ppm, which may seem low, but it's not, and it's increasing. This is a graph of possible scenarios up to the end of this century, according to the IPCC, the last report. And you see that if you continue emitting CO2 to the atmosphere as business as usual, you probably follow the pathway number 5 in this graph, and you have an increase in the average temperature of the planet by more than 4 degrees, and this is for the best extrapolation, the best scenarios. Only in a pathway, the pathway 1 or 1A, you be within the agreements that the nations have done to have an increase of a maximum of 2 degrees, 1.5 to 2 degrees. And this means that you have to reduce the emissions right now, not very far away from where we are now, including to have negative emissions by 2050 or a little bit beyond that, but before the end of the century. So this put this subject of CO2 capture and utilization, and as well as hydrogen and other sorts of decarbonization in the top of the subjects that we have to do right now. So the concept of CO2 capture and conversion, or capture and utilization, is very simple. You just capture CO2 either from industrial source, like for a stationary plant that burns fossil fuels, or from the atmosphere, where the concentration is much lower, but this is possible. I will briefly mention about that. Okay, and once you have captured the CO2, employing especially renewable energy and other reagents, you transform the CO2 molecule into some products that can be either used to produce goods, to produce plastics, for instance, that and then you have the carbon stored, or fuels that will be used to generate energy, and the CO2 emitted could close the cycle, be recaptured and reused. Okay, so this is a concept of CO2 capture and conversion. That is a little bit different from CO2 capture and storage, that you do not transform the CO2 molecule, but just storage it in underground or something like that. Well, let's talk first a little bit about CO2 capture. There are basically 4 ways to do that. Absorption, that it's a commercial technology that use liquids, normally basic liquids like amine solutions. Adsorption, that I will mostly concentrate my talk on that, that involves a material, a solid materials, an adsorbent that capture the CO2. Cryogenics, that is not very popular, and that involves temperature drop, pressure swing to condense the CO2, and membrane technology that is also used commercially in some cases, but I will not talk about that. I will mostly concentrate in adsorption to show you some of the developments that we are doing in this field. You can think about materials to physisorb, for a physical adsorption of CO2, and you can think about zeolites, metal organic frameworks, different kind of MOFs have been used for that. Those materials have high specific area, but are not selective. They can work well if you have a concentrated gas stream with CO2, because the interaction involves only physical interaction. It's not a chemical interaction. But you can develop materials to can absorb the CO2 molecules. Normally, you functionalize a materials with basic molecules. CO2 it has acidic properties, so in order to react the CO2 molecule with the surface, usually a basic property is required. Normally, these materials have lower surface area compared with the MOFs, with the zeolites, higher heat of adsorption because it's a chemabsorption and not a physical interaction, but they are very selective to CO2. And this is very important in some issues, especially if you want to capture it directly from air, where the concentration of CO2 is too low, is very low. Well, we are studying materials, functionalized materials for CO2 capture based on chitosan. Chitosan is a biopolymer that has some amino groups on it. This is a part of the structure of the polysaccharide, and it can be obtained from crustacean, not like crabs and other crustaceans. So it's a byproduct of the fishing industry, let's say. So we have it available here in Brazil. It's not very expensive. And what we do is to try to carbonize this chitosan in order to produce materials with high surface area, high porosity, but still being very active for CO2 capture. We can do hydrothermal carbonization, that is a carbonization in the presence of water, so the temperature is not very high. But we also do some thermal carbonization, activated carbonization with some activated agents. And I will show some of the results that we have. Here's a table of some of the materials that we prepared. You see that chitosan have a very low surface area and absorbs very small amount of CO2. Although chitosan has a lot of basic groups, the area, the exposed area is not high enough, and we do not capture very much CO2. But upon the hydrothermal carbonization, is the HTC, that, as I mentioned to you, is carried out in the presence of water at not very high temperatures, around 108 degrees. Although the area did not vary very much, but we may increase by fourfold the amount of CO2 that was captured. But these results are not very impressive. What we have done later was to try the carbonization in the presence of potassium carbonate at very high temperature, 600, 700, and 800 degrees. We still have a reasonable amount of nitrogen on the material. Now you lose some of the nitrogen when you carbonize, you become a more polyaromatic structure, but you still have some nitrogen atoms on the structure of the char, the biochar that is formed. But you can see now that the area is significantly increased, as well as the amount of CO2 uptake. These numbers here refer to pure CO2 at 25 degrees and 1 atmosphere. It's just for a benchmark, okay? And here in green, we have a combination of HTC. So we firstly carried out hydrothermal carbonization of chitosan, and then we carbonized at high temperature the material. So you combine both methodologies, okay? And again, we still have a very high surface area. We still maintain most of the nitrogen atoms in the materials, and we still have a very high CO2 uptake, okay, for the benchmark comparison. Normally, people say that above 4 millimoles per gram, you can consider a material of high efficiency for CO2 capture. So this is part of the study that we are doing here in our group on CO2 capture. And we intend to use this to capture CO2 directly from air. This is an example of a device that can be developed to capture CO2 directly from air. I will not go into details, but you have an airflow. Firstly, you have a desiccant to withdraw water, and then you have the CO2 adsorbent that must be composed by functionalized materials. In terms of conversion, we must bear in mind that CO2 is a very stable molecule with an enthalpy of formation of minus 94 kilocalories per mole. And in order to, for instance, to reduce the carbon atom, must input energy. And if you go in this direction to produce carbonates, for instance, there are some thermodynamic concerns. We can produce some fuels like methanol, dimethyl ether, hydrocarbons, or organic carbonates and olefins. Let me briefly show you some of the results that we have with the methanol. The CO2 hydrogenation to methanol is normally carried out over copper zinc oxide catalysts. They are active, but work in the thermodynamic limits at 270 degrees. we were able to find a formulation of the catalyst that was active at 250 degrees. This dotted lines here denotes the thermodynamic equilibrium. And we are working on different kinds of promoters to improve activity and selectivity. But we must bear in mind that to produce this catalyst with promoters, we have to study it very carefully, because what is important here is the aging, because we need to have a crystalline phase of Zincyan malachite. And we have observed that depending on the conditions that you do for the aging, and with the promoters that we have, magnesium, barium, calcium, we need to study the specific conditions in order to observe the Zincyan malachite phase. You can see here that in this case here, we did not form the Zincyan malachite, but here, when you change the condition, we did form. Another important chemical is DME, dimethyl ether. It's used as a substitute for diesel or diesel oil in buses and trucks. It's a very clean fuel, burning without having pollution. Okay, and we also studied the direct conversion of CO2 to dimethyl ether over bifunctional catalysts. The catalysts that have a metal function and an acidic matrix. Here, you can see that alumina as a support gives a higher selectivity to DME compared with niobium oxide, okay? And we could increase this selectivity by modifying this aluminum with some silicon atoms that we have stronger acid sites. And you can see that when you compare these two catalysts here and here, you see a higher conversion and higher selectivity to DME. So it can be produced from one step. And the final part of my talk will be on organic carbonates. They are very important chemicals used in different kind of utilization. And we have studied the impregnation of potassium iodide on zeolites to produce cyclic organic carbonates. We have studied as a model reaction the production of styrene carbonate, and compared to potassium iodide alone, that it's believed to be one of the industrial catalysts used in this process. There is an industrial facility in Taiwan to produce cyclic organic carbonate that is believed to use potassium iodide. And you see that impregnated it in the zeolite, you have a much higher activity. Here is some of the results that where we vary the amount of potassium iodide that we impregnated, and you see that the conversion increase as well as the selectivity. And the reason for that, we have performed some DFT calculations, and we found that the activation energy for opening the epoxide ring is perfectly fit, and the transition state perfectly fits inside the zeolite. Here is the potassium iodide alone. So we believe that this is a kind of enzyme mimicking of the zeolite that allows the perfect fit of the transition state. And in terms of aliphatic carbonates, we have a very strong thermodynamic constraint. So the reaction, for instance, to produce dimethyl carbonate is not favored by thermodynamics. So, and is not kinetically favored as well. So mostly we use metal oxide like cerium oxide. And here are some of the results that we have on this reaction. I will not go into details, but we have doped the cerium oxide with a small amount of copper, and we found that the selectivity to dimethyl carbonate it was higher, especially when we dope with small amount of copper. And we have correlated this to the presence of oxygen vacancies on the structure of the silicon oxide. And to prove that, we have prepared some nanostructured silicon oxide with different concentration of oxygen vacancies. And you can see that one of the species like that, with this kind of facets, exposed facet, was more active. And that was the one, this was the one that has the highest concentration of oxygen vacancies. So we proved that oxygen vacancies are important in the activity of the catalyst. And we also showed by calculation that the 110 plane was the one that better absorbed the CO2 to form a carbonate intermediate, okay? So completely correlated. Just to show you how you can shift the equilibrium of the reaction by putting in the medium something that reacts with water to shift the equilibrium. So you have using methyl trichloroacetate to shift the equilibrium, and we have shown that this molecule reacts much faster with water, hydrolyze much faster than the DMC itself. So it could be a good candidate to shift the equilibrium, and especially the carboxylic acid form could be transformed back in the methyl trichloroacetate. And this has proved to be correct when you compare the same reaction to produce DMC. This is a silicon oxide without any kind of dehydrant. You have a very low conversion. And if you put some of this is a very common compound used in this kind of reaction to shift the equilibrium. And what we have suggested is much better. The same with the silicon oxide doped with copper. And finally, these are some of the last slides, just to show you that hydrocarbons can also be produced from CO2, and you have to combine. You have to first convert CO2 to carbon monoxide, and then you go to Fischer-Tropsch, where you oligomerize the CO and hydrogen to hydrocarbons. And you can, depending on the conditions, depending on the catalyst that you use, you can produce aviation fuel, diesel, or even olefins that are raw materials for the production of plastic. Here I show you some results that we have, mostly focus on the production of olefins, C2, C4 olefins, and we have found a formulation here with a very interesting selectivity and a very interesting conversion to lower olefins, now working at atmospheric pressure. If you increase the pressure, then you go to higher hydrocarbons. And this is the concept of the power to liquids, PTL, where we capture CO2 directly from air using some kind of functionalized materials. Produce hydrogen from a clean source. You can use biohydrogen, but you can also produce it from water electrolysis using renewable energy, or even photocatalysis. I'm working on photocatalysis and photoelectrocatalysis to produce hydrogen. And you can hydrogenate it to methanol and DME. This is the object of a project that we have recently approved here in the State Foundation of Rio, or hydrocarbons that we are involved with the production of synthetic aviation fuel in a program that is a collaboration between Brazil and Germany. Well, this is a picture of the group before the pandemic, of course. You have here my contacts. There's some of the financing that we have all over the years. And just to end my presentation, I think that the sustainable development must be achieved if you have a very good education, if you educate our students. Okay, with this, I end my talk. Let me stop sharing here.
I couldn't agree more. Yes. we need to take care of our children and our planet. So thank you very much for your talk, Professor Claudio. We are going for the next talk, and then in the last part, we are going to have a discussion. So I'd like to welcome very much my colleague of my Department of Physics, Professor Marlus Koehler. He is a bachelor. He has a bachelor's degree in physics at Federal University of Paraná in '94, master degree in '96, and a PhD in physics at Federal University of Santa Catarina in 2000. He conducted a postdoctoral studies from 2002 to 2002 at Swiss Federal Institute of Technology, ETH, in Zurich. He has been an associate professor at Federal University of Paraná since 2005. He has experience in the field of physics with emphasis on charge carrier transport of conjugate polymers, charge carrier injection, organic devices, organic photodiodes, and organic solar cells. And also some interest in using cellular automata to model complex biological and social systems. So I welcome you, Professor Marlus, and to give your talk, and then in the end we make a discussion. Is that everything okay with your sound? No, you are muted.
Okay, now.
Okay, very good. Yeah. Thank you. You can start.
Thank you, Lucimara, for the nice introduction. Thank you, the organizers, for the opportunity to speak in such a high-level event. Okay, I will talk about very quickly about the advances in organic solar cells. Since we had a very nice talk this morning, I will not enter in details. Okay, organic solar cells are an alternative to harvest solar energy. But the organic solar cells, let's see what happens. Okay, but organic solar cells are not going to replace silicon solar cells, but find applications where silicon solar cells are not convenient, because silicon solar cells used to be heavy, rigid, not flexible. So organic solar cells, on the other hand, can be flexible, can be printed in large areas, use soluble processing methods, can be low cost, can have a nice integration with the architecture of the buildings, can be put on windows, can be put on a facade to produce energy. And also, organic solar cells are very suitable for portable electronics, so that you can see here is a chargeable, it's a device to recharge your mobile phone. So organic solar cells are very convenient for those kinds of applications where silicon are not so nice. Okay, but there are problems with the development of, to develop this technology. One of the, okay, let's talk about the problems later. Okay, let's say that organic solar cells are based on organic semiconductors. Organic semiconductors can be divided in two kinds, one small conjugated molecules or conjugated polymers. What we say that these semiconductors are organic because those molecules are based on carbon, on special carbon with a special hybridization, the sp2 hybridization. And this hybridization produces alternating single and double bonds, as you can see here. I don't know how to minimize here. Okay. As you can see here, you have alternating single and double bonds along the molecule or along the polymer, and this alternating single and double bonds produce the nice fancy electronic properties of those materials, so that we can use those materials to produce electronic device, and in this special case, to harvest solar energy in order to produce a solar cell. Okay, but let's back to the problems. One of the great problems with those materials is that when we shine light to this material, you do not create free charges. Instead, you create an exciton. You excite here the electron from the HOMO of the material to the LUMO of the material, so that you have a positive charge in the HOMO and a negative charge in the LUMO. But this, since those materials have a very low dielectric constant, the Coulomb attraction between the electron and the hole create an exciton. And we have to dissociate those excitons in order to produce electric current. Because this dielectric constant here is low compared to inorganic semiconductor, for example, this binding energy, the exciton binding energy, is very high. So it's very difficult to separate the electron in the hole to create free charges. Instead, what we have when we illuminate organic semiconductor, you create the exciton, but the exciton recombines and you have light back. You don't want light back, you want charges, free charges to produce electricity. Fortunately, in the early 19th, people discovered that when you mix two kinds of organic semiconductor, one organic semiconductor with a low ionization potential that we call donor, usually it's a polymer, with another organic semiconductor that is usually a molecule that has a high electron affinity. When you create the exciton in the donor, this exciton tends to diffuse, eventually will diffuse to the interface between donor and the acceptor. And then if this difference in energy here is suitable, you can have a very fast electron transfer from the donor to the acceptor, so that this transfer can dissociate the exciton, and it will free the charge and produce current. Okay, but for this to happen, you have to have this driving force that we call here higher compared to the exciton drive, compared to the exciton binding energy. When you have this electron transfer, you say that we quench the exciton, we separate, we split, we dissociate the exciton. For instance, in this experiment here made in the Lucimara's lab, nice experiment, if you take a polymer, a single polymer, this guy here, the donor, and you illuminate the donor, you shine light on it, you have light back, you have a photoluminescence. But if you mix this polymer with a fullerene, for instance, this guy here, this molecule that has the shape of a soccer ball, you do not have a light back anymore. So that you quench the extra work, quench your photoluminescence, you say. So it's very important to have this difference here high, but not so high, okay? So how does these materials, these organic solar cells work? Okay, the first organic solar cells that use fullerene, these guys here as acceptors, they have this mechanism of electricity production. Okay, the donor absorbs the light, you produce here the exciton eventually recombines, but or eventually diffuses and reach the interface between donor and acceptor. You have this very fast electron transfer from the donor to acceptor, and then you separate the exciton and you create free charges, electron current here in the acceptor and a whole current here in the polymer, so that you from this photon here you get free charges. But the bottleneck of those devices is the fact that this exciton diffusion length is very, very, very small, in the order of 10 nanometers. So you have to increase the probability that these excitons will eventually, once absorbed by the donor, will reach the donor acceptor interface in order to transfer the electron and dissociate the exciton. So the best structure to improve this transfer is what we call bulk heterojunction, where we mix the acceptor, we make this acceptor soluble. Okay, the chemists are nice to do that. They make this guy soluble. You mix with a polymer in a solution, evaporated solvent, you have this nice structure here, mixing both donor and acceptor, so that when we absorb the photon, you create the exciton. Exciton has a higher chance to reach the donor acceptor interface and then produce free charges. Okay, but what we saw, this is a table showing the efficiency of all organics, all solar cells And we see here is the evolution of the efficiencies of organic solar cells. What we saw, this is until 2017. What we saw here is that we see an improvement in the efficiency of organic solar cells, mainly because chemists are were very nice to synthesize new donor materials, very efficient donor materials with a nice band gap, so in order to absorb better the solar energy, so that the whole efficiency of the device increases. But when we reach here, 2011, we find a plateau here in the efficiency. The efficiency of those devices stagnates here around 12%. Why that? Basically because of those guys here that were the acceptors at that time, the fullerenes. When we have the fullerenes, what you observe, the measure of the major cells was a trade-off between two very important parameters for the mechanism, the functioning of the solar cells. Those parameters are those guys here. We can see here in this graph. These are the short circuit current, this guy here, and the open circuit voltage. This is a cell under illumination. You have this current voltage characteristic here. From this view here, you can get this guy and this guy. Roughly speaking, in a simplified way, the efficiency of the solar cells depends on the product between the JSC and VOC. And what happened for solar cells based on fullerene was the fact that when we got a very high current density, you got very low VOC. So you have a negative trade-off between VOC and JSC, so that efficiency stagnates around here. But once you have a very nice solar cells that could separate, dissociate electron, produce charge, we lose open circuit voltage. Why that? Simply because, as you told you here, you need a driving force here to separate the exciton. And if you separate the exciton very efficiently, you produce a nice current. But when you have a very high driving force, you makes this effective gap of the materials, that's the energy difference between the HOMO of the donor and the LUMO of the acceptor, very narrow, and this decreased the VOC. So the efficiency of solar cells based on fullerene were trapped in this region here of this space here, voltage current. But research are nice, and people discover something very, very interesting. They discover a new acceptor. They are called no-fullerene acceptors. And with those no-fullerene acceptors, they were able to escape from this region, this area here, escape from this negative trade-off between VOC and JSC, so that these people could find a very nice solar cells with a very high VOC and a nice current density. So why that? Why that? The advantage of these guys, they achieve this because these non-fullerene acceptors that are here, I have a family of non-fullerene acceptors. Here are the two state-of-art fullerene non-acceptors, non-fullerene acceptors, Y6 and Y7. Okay, these non-fullerene acceptors, this kind of molecule here, they have a high absorption coefficient, what the fullerene does not absorb in the visible range, but those guys absorb in the visible range, so that they create a second channel for photocurrent generation. They have lower VOC losses. I will explain why. They have, they can be the primary low band gap light absorber, what didn't happen with the fullerene. They have improved morphological stability. They are easy to synthesize. Okay, the chemists say that, I'm not chemist, but they are easy to synthesize. And nicely, they have tunable energy level, so that the chemists can change some chemical groups here in the molecule, so that it can tune or fine-tune the energy levels in order to absorb more light or in order to improve the charge transfer. Okay. So now what happens is that with a non-fullerene, we have the absorption of the photon in the acceptor. the diffusion of this exciton to the interface between the donor and the acceptor, and the transfer of the hole from the acceptor to the donor, and dissociation of the exciton in the production of free charges. Okay, in order for this transfer to be efficient, we have to have this driving force here higher than the exciton binding energy. And this is a very important fact for these non-fullerene acceptors. They have low binding energy, so that you can have an efficient hole transfer with a small driving force, so that we preserve here this energy difference between HOMO and LUMO, so that you can achieve higher VOC. Okay, when you see now the full table until 2020 of 2021 of the evolution of the efficiency of organic solar cells, you're going to see you have the plateau here, but from 2017 ahead, you have a real increase, very steadily increase here in the efficiency of the device. Until now, we reached something like 18% of power conversion efficiency in those devices. Yes, the highest today. Why? I explain why. If you see here, the absorption of blends of the conjugated polymer with one non-fullerene acceptors, the ETIC here, this guy. And as you can see here, the absorption of this blend is very broad compared to the absorption of the blend that uses fullerene. Here, the absorption of the blend with fullerene is very narrow. So you have just a narrow range of energy where you can absorb the solar emission. With these guys here, with this ETIC, we can absorb in a broader range of wavelengths. So you harvest better the solar energy. This is one reason why those guys improve so much the efficiency of the organic solar cells. Another reason, and a key reason, is that those guys, these non-fullerene acceptors, they have a group here that are a donor group. They have internal charge transfer inside the molecule. They have, in the middle, you have a donor group, and at the edges of the molecule, we have an acceptor group, so that you have an internal charge transfer inside the molecule. And this internal charge transfer tends to localize the HOMO of the molecule here and the LUMO of the molecule at the edges. So that when we excite this molecule, you separate in some way the electron and the hole. The hole stays here and the electron goes to the edges. So as you separate the charges, you remember the Coulomb law, you decrease the binding energy. If you compare the binding energy of these non-fullerene solar cells, these non-fullerene acceptors with the binding energy of fullerenes, you see here that fullerenes have a much higher binding energy. So you need a very high driving force in order to dissociate the exciton. This is what it doesn't happen with those guys here with the non-fullerenes, because non-fullerene acceptors have a very low exciton binding energy compared to the fullerenes, so that you can more easily dissociate your exciton. You don't need a very high driving force, so you do not lose too much VOC. Here we can see the distribution of the HOMO in LUMO. You see that in fullerenes, the HOMO and the LUMO are more or less evenly distributed along the surface of the molecule, let's say, surface, okay, along the structure of the molecule, so that you have a superposition of the electron and the hole that increases the binding energy, the exciton binding energy. But in those guys here, on the other hand, you have a separation, a spatial separation between the electron and the hole, which decreases the exciton binding energy. So I'm already late. Okay, let's go to the next. Okay. Okay, what we also observed that is a superposition between the emission of the donor and the absorption of the acceptor in those solar cells based on non-fullerene acceptor. so that we absorb now the light here in the donor, but the donor transfer the exciton to the acceptor, and then from the acceptor you have the dissociation of the exciton. So you have these two channels. You have the energy transfer from the donor to the acceptor, and you have also the the absorption in the donor, either in the donor or in the acceptor. But when the light is absorbed in the donor, it transfers the energy to the acceptor, and then in the acceptor, the exciton is dissociated by Hall transfer. Or you can have your photon absorbed in the acceptor, and then the exciton is dissociated by Hall transfer. There are another nice, fancy application of organic photovoltaics. This is one if you have two materials so that you have a high absorption selectivity, so that you can absorb photons in the infrared or in the ultraviolet, but you transmit photons in the visible range. You can fabricate very nice solar cells, or transparent solar cells, so they can put in your window. You have the production of energy, and simultaneously you illuminate your environment. Another interesting application of organic photovoltaics is the possibility to use indoor light source like LEDs or like the fluorescence lamps to produce energy to off-grid displays that are Wi-Fi connected to a network, so that you can use those cells to capture this light and feed those devices, these portable devices or devices that are connected to the internet, the off-grid devices. Okay, Federal University of Paraná is a pioneer in the use of organic solar cells. Professor Lucimara has this nice project with with the Copel company, local power company. You have these organic solar cells on the windows of our exact science building in our campus, and also on the ceiling of our building. And then they also have this project, very nice project with the Curitiba City Hall to install these organic solar cells on the surface or on the ceiling of this bus stop tubes in order to generate power here for these bus stops of our public transport system. Okay, concluding now, organic solar cells are becoming a viable alternative as a renewable source of energy. The application or discovery of these non-fullerene acceptors dramatically improve the efficiency of organic solar cells. This minimum driving force strategy, use it if those guys here, those non-fullerene acceptors, change the way those cells work. Now, the donor now is a kind of die, is a kind of antenna to capture the light and transfer the exciton, the energy to the acceptor. Now, energy transfer and Hall transfer are fundamental. And the research on this field is very nice because it's a funny way to study basic photophysical properties of conjugated molecules. Okay, acknowledgements now to Lucimara, Professor Lucimara, to Leandro, to Kleber, all the people here. And thank you very much for your attention. I'm sorry for the time.
No, we are actually in a good timing still.
Okay.
Thank you very much for your talk, Marlus. Yeah, we are partners for many years, so it's nice to hear. And now we are going to move. So please wait for the discussion, Marlus, in the end of this section, okay? And we are going to move to our last presentation. That is Professor Gustavo Henrique de Oliveira. And Professor Gustavo, he is a professor also here in Federal University of Paraná. He has her electrical engineer degree from Federal University of Juiz de Fora in Brazil, and his PhD degree in electrical engineering from Unicamp. And also the University of Nice in France in 1997. Since 2009, he is an associate professor with the Electrical Engineering Department at UFPR. And his research application include power transformers, instrument transformers, and frequency-dependent network equivalent modeling, mode estimation, and monitoring the electrical power systems from PNU data, inverter-based control at distributed and renewable energy generation. So very welcome, Professor Gustavo was the coordinator of quite nice big project here in the university. So let's hear about your research, Professor Gustavo. Welcome. I was also muted. Now you are muted. Now you are on. Oh yeah, sorry. Let's see if the screen is sharing.
Okay. Thank you very much, Professor Luis, Professor Lucimara, and the organizers for the invitation and for the opportunity to be in this interesting section. I will share my screen. Okay. So, are you seeing my screen? Okay.
Yes, it's very good.
So, clean energy is the main topic of this section. And as we have seen before, we have many points of view related to clean energy. And when we think about clean energy, the image that comes up to our mind is green picture of these solar panels. But in our research area, we frequently have in mind this second picture, the energy flowing from the source to the consumer that should be in good standard of electrical power quality. And take a look at this picture here. Now, in the left, now we have something that it will be okay, now it will be clean, and in the middle, what usually are not. Unfortunately, when we have the solar panel, solar power plant on the left and the consumers on the right, it passes through these inverters, and the energy tends to be more like this one here. So we reach to the supraharmonics. And what is supraharmonics? Supraharmonics are distortions on the current and voltage signal in a frequency range that is higher than regular harmonics. And people are still working on regulations since these subjects are pretty new. And supraharmonic can be a problem for an electrical equipment and so to the consumer. Here we can see the standard that we have about the regular harmonics and the range of the supraharmonics. So the root of the phenomenon, the supraharmonic phenomenon, is the switching operation that are within the inverters that are necessary to recover a sine-shaped voltage and current that is given to the grid. Now here's the representation of the solar plant. On the left, we have the panels, and on the right, we have the grid, and the supraharmonic start right here, where the red arrow is pointed at. Okay, so we like to further investigate this subject. So in the lab, we have a setup to study inverters that emulate all the system. We can emulate the solar panels, every different kind of solar panels. We emulate the grid, the consumers, and we can put the inverter in the middle, as you can see in this photo. So we have done measurements using this inverter here to see what's happened. And in these pictures, we can see the current signal provided by the inverter. And the interesting is the Frick's domain version of this signal. And here we can see clearly the presence of supraharmonics between 10 and 100 kilohertz. Here, more like here. So once the superharmonic is generated by the inverter that we can find in every solar plants and such kind of generation, it flows from the system, passing through cables, transformers, instrument transformers, and so on, reaching to equipments and reaching to consumers. And due to this path that superharmonic has in the system, it can be a source of many differences in the electrical system. And we can see amplification through the instrument transformers, voltage, potential damage to the connector instruments, amplification through the power transformer to the power grid, power transformer lifetime issues, interaction between the transformers and the cables, interaction inside the power plants. So we put a spot on the first topic that we would like to talk about again. And here we are again in our lab. So what we have done here is to get measurements, to get a precise wideband model of instrument transformers to see how the superharmonic propagates through them. We will not go into much into the details. It's not the subject of this talk. But we have more or less this kind of measurements of the equipment. And here we have the result. Now, what we can interpret on this picture on the right. So until a certain degree of frequency, the instrument transformer do his job. But when we are in the range of superharmonic, we can see a huge amplification in the frequency domain. And if this huge amplification reach the equipments that are connected to such kind of instrument transformer, we can have damage. So by studying this kind of phenomenon, we can mitigate its effect on Myanmar or even avoid it. And on our campus, on our power plants, we have a possible situation. We have solar plants, we have inverters, we have transformers, we have cable, we have all the ingredients of the receipt. So to analyze that, we have made some attempts. We went to the power plant, we have done some measurements, and here we can see the photo that we have worked on that this day on that, and we are still working on this subject. So to summarize, the idea here is to bring a different perspective about clean energy. We have the perspective of the environmental environment, we have the perspective of physical studies, and some perspective on electrical engineer side. So thank you very much, Professor Lucimara, Professor Luis, and the others.
Thank you very much, Professor Gustavo. It was a very nice talk. Now we are going to open for a discussion. And today we had the opportunity to walk through the many ways of generating energy, hydrogen, biomass, OPVs, and then when the electrical energy are on the systems, all the aspects of the transmission, delivery, energy loss, it's a challenge in all areas. So we need to work together. So I call out Professor Luis, you are already here. If Professor Gustavo, Professor Claudio, Professor Satinder could open the microphone, maybe we can have a little discussion before we finish our panel.
Okay, maybe I will start the discussion. First of all, I'd like to thank the presenters. You know, they have given excellent contributions to the meeting, and of course, it was a pleasure hearing you all. But in terms of questions, I reserved one question for Professor Satinder and one for Professor Mota, and eventually later another one for our electrical engineers regarding solar panels. Professor Satinder, if you could, are you with us?
Here, I'm here.
Okay, thank you very
Sorry.
much. Thank you
I'm
very
here.
much.
Yeah.
All right, so you mentioned about inhibitors from lignocellulosics for hydrogen production. And I mean, I always expected that those specific inhibitors that are known, for instance, in cellulosic ethanol production are not so critical for dark fermentation. So could you comment on what are the keys, the key inhibitors from lignocellulosics towards hydrogen production, and what is the kind of pretreatment that we are talking about in terms of generating those those inhibitors?
You're right, Professor Ramos. Thanks for that question. It's not the lignocellulosic-based inhibitors which are actually inhibiting the productivity or production of hydrogen. It is because, for example, in dark fermentation as well, you have so many other products, okay, the byproducts, which act as inhibitors directly. So I'm not talking about the lignocellulosic based, like, you know, you have furfural and HMF and all that, but rather, you know, other products. For example, you have these, some of the other organic acids which are present. Okay, acetic acid is good. Of course, it can get transformed into, you know, one of the volatile fatty acids, which can get transformed to hydrogen in the presence of light. But then you have other organic acids, okay? For example, in our case, when we were doing the research, okay, specifically with respect to hydrogen production, we saw that sometimes butyric acid was inhibitory, you know. It was, if there was a lot of butyric acid, then it was affecting the hydrogen productivity. So, so I'm not referring exactly those inhibitors, but then going back to the pretreatment, we have seen that pretreatment plays an important role also, because you know that when it depends on the type of pretreatment, if it's acidic, alkaline, the convention type, then you know you're introducing so many other factors, and of course you simplify the biomass, but at the same time you enhance the production of so many byproducts, which would rather, you know, inhibit the biohydrogen production. So methanol, for example, in our case, we saw in one of the pretreatments, of course, we did not work directly with wastewater, we were more crude glycerol based. So we saw that crude glycerol has methanol, and more so with one type of pretreatment, the methanol concentration increased, and then the hydrogen production was reduced as well.
Interesting.
So
yeah,
that kind of innovation.
In this innovation world, there's also the synergy among different minor components that this makes this a whole mess, very difficult to tackle. Exactly. And since we're discussing, let me just hook into a comment that you just made. You talked about crude glycerol or crude glycerin. Now, crude glycerin can vary a lot. So what is the type of crude glycerin that you're using? You know, because I mean, depending on the technology that's used to produce biodiesel, crude glycerin could come with soaps, alkaline metals, could come with a whole lot of other stuff, including methanol, which is, as you just mentioned. Mm-hmm. And methanol in crude glycerin is an inefficiency in the whole process, because you cannot produce methanol. So could you just make a brief comment on what is crude glycerin for you guys in Canada? Because, it could be an interesting comparison point to what we have here in Brazil.
Okay. Yes, interesting question. Although, it's very sad to tell you that the biodiesel plant, which was operating in Canada, it recently closed. It's so unfortunate, I don't know in terms of scale of production if it was not efficient for them, but okay, let me walk you through the process. So they used to take the animal fat, okay, and then transestrify that and produce the the biodiesel. So the crude glycerol that we used to get, the methanol concentrations were pretty low, okay? But you're right, once we obtained a sample from US, they had a biodiesel plant operating there. It was based on vegetable oils, okay? And somehow the methanol content was pretty high there, and our crude glycerol based biohydrogen production was not at all comparable in both cases. Although the byproduct, that is crude glycerol, comes through the same process, that is transestrification, to produce the biodiesel, right? But you're right. So this is very unfortunate. And to tell you very honestly, now, if I need crude glycerol here in Canada, we don't have a supply. So we have to go to US. It was a big plant, in Canada. They were meat producers, and they were, extracting that fat, animal fat, and transforming it into biodiesel. But
yeah, I'm sorry
unfortunately, it closed. Yeah.
Okay, thanks a lot for your answer.
I think we, sorry to add here, we have a lot to learn from Brazil for biofuel, Canada. Because even our bioethanol, we have one greenfield ethanol company here. It's called Greenfield Bioethanol Incorporate. They are also struggling at this point. Okay, since I work with industrial sector, I happen to hear this, and which is unfortunate. I don't know why it happens. I don't know if it's the temperature here versus Brazil.
Well, so that could be an issue.
Yeah. So, yes. Okay. Thank you.
Thank you. Professor Mota, in one of your tables regarding CO2 absorption, I noticed that when you thermally treated your material to produce an adsorbent highly efficient for CO2 retention from chitin, I cannot see a correlation with nitrogen content in it. It was not. I know that this takes part of the whole picture, but it was not the nitrogen content, because sometimes the nitrogen content would go up and absorption would not. Sometimes the surface area would go up, but absorption would not necessarily go up. So I'm curious to hear from you what other factors are actually involved in this CO2 absorption based on chitin. Thank you very much. Your mic is off. Could you turn it on, please?
Yes.
Thank you.
Sure. Thank you, Luis. We are just trying to understand some of these results, because we use pure CO2. Okay, so we have both chemisorption and also physisorption. So of CO2, we did not test in a blend with other gases. So that's why sometimes we do not see a good correlation with the nitrogen content. I express the nitrogen content in terms of carbon-nitrogen ratio, and I did not put the absolute value of the material. But we are still trying to understand a little bit better these results. because sometimes you have fluctuations that occurs. I don't know, maybe I have to check about that, because we had a way to prepare the materials using quartz glass, instead of stainless steel, in order to calcine the material. And for some circumstance that we do not know exactly why, when you prepare it in quartz glass tubes, the results were much better. I don't know if this has something to do with sometimes when you use here high temperature carbonates, because we put potassium carbonate, perhaps some kind of dissolution of attacking of the quartz glass may occur. We do not know exactly. So we have to certify that, because I know that when we prepare the materials in quartz glass for the calcination, the results were a little bit different when we prepare in the stainless steel. And I'm not sure if I have mixed that then, okay? This may be a problem.
Interesting. Thank you. I don't know if we are having a lunch effect around here, because so far no questions have arisen. So I will go ahead and try to motivate another discussion here regarding the solar panels, the photovoltaic panels. And so the question goes to Marlus and Gustavo. First of all, thank you very much for your contribution. When I was listening this morning to the talk given by Dr. Zhang, I was kind of moved to forward the following question to her. Could lignin or technical lignins be used as a polymer acceptor? And by looking at your material today, Marlus, I noticed that your non-fullerene materials, they contained a considerable amount of oxygen, right? So, you know, functional groups that contain oxygen, and it's not surprising that they are better, they'd have better properties in terms of conductivity. So are you aware of any study utilizing renewables to produce polymer acceptors for these applications?
Yeah, I heard that people are trying to make a polymer device. Okay, instead of using a single molecule, they use also a polymer as acceptor, and using more or less the same chemical groups that you have in these small molecules. Okay.
Cool. Yeah, because when we do a lot of thermal analysis, as you know, thermal processes to convert biomass into chemicals and fuels, and we also play a lot with pre-treatment, as you must have noticed when I spoke to Dr. Brar about pre-treatment influences in hydrogen production. But we know from those studies related to carbohydrates that humans are produced, and humans are furan polymers that have no use whatsoever nowadays. I mean, very limited use, and they are considered like a byproduct. So anyway, it's very easy it's almost like carbonizing sugars to produce an intricate polymeric structure that contains oxygen in its structure. And I don't know, Claudio, don't you know that have you ever seen any work related to the application of humans, like furanic polymers in this conductivity area? I mean, anything in that line?
In conductivity, no, I'm not sure, Luis. I know that people use a kind of biochar made by biomass also for CO2 capture, but conductivity, I'm not sure about that.
Yeah. I've seen biochar applications for that purpose too, and it's pretty much the same. I mean, what you get out of thermal dehydration of polysaccharides or sugars is a biochar. You know,
yes.
Humans are components of biochar anyway. So I see
the problem is that they are normally only physisorption, because most if you use sugar, only sugars, you do not have very high basicity for specifically capturing CO2.
I see. All right.
By the way, Professor Frank is in audience. Maybe she's
Is she in the audience?
Yes. Okay. But you see, that in those kind of cells, one problem is the morphology. And if you have a small molecule, they tend to aggregate. And then when they aggregate, they decrease the surface of the external dissociation. So this is a problem, the durability of those devices. So that's why people is trying. But I'm not so familiar with the chemists because I'm a physicist.
It's okay. I'm sorry about that.
Yeah, oh no, yeah. But you see, the major part of this chemical group, then you need something like involving thiophene. And it's organic with carbon, but you must have the sulfur there, this pentagonal ring to make it an acceptor. As you see, even in the fullerene, if you see the structure of the fullerene, you have hexagonal rings and pentagonal rings, and then pentagonal rings create the high electron affinity that you need for accept the electron. Okay.
I see. Cool. Okay. Do we have any questions in your chat? I don't think so. I haven't seen any. Have you?
No, not really. No, but we are ending actually. We are arriving to the end. So if there is someone would like to make a question, not using the chat, but open the screen, we can also have a picture, please.